So we have v minus e plus f equals to 2, which is true for all planar graphs, both simple or multi. So being true in multi means that you have more than one connection between two vertices. So you can have a graph with two vertices and two edges as simple as this. That would still satisfy that. As you can see here, there are two edges, two vertices, and one and two face. Make sure that you have the outside as counted as one face, okay? So that's true. But the inverse question is actually the more interesting one. So if somebody gives you a graph, how do you know if it's planar or not? And I gave you a criteria called Krotowski's theorem, which says only when you have a subgraph that looks like a K5 or K33, then it's non-planar. If it's free of those, then it's planar. That was it. But often that's not so easy to see. So instead of that, there's a way to use this identity to a graph to see if it's planar or not. Okay. Now, there's a big problem with using this, however. See, you can only use this if you already know the graph is planar. Okay. Now, you know, as we've seen this example, here's K4. So you have four vertices and several edges. And if I draw it like this is not planar because these two edges overlap each other, right? But we can definitely make a isomorphic version of this graph where it's connected like this to make it planar. And of course, if it's connected as a planar graph, then we can definitely see that this holds. But you wouldn't know if this is true or not unless you know it is planar, right? So at first it doesn't make sense that we can use this for planar. But here's a way to think about this. If the graph is simple, so let's think about the case when we have simple graph, then we have the fact that any face is surrounded by three or more edges. Now, if you go back to the example that I showed you, the simplest multigraph, this case, you have two vertices and edges like that. You can see that this face right here, this face here has two edges, right? Yeah. So you can easily see that if you have a face that's surrounded by only two edges, that means you're connecting two vertices by more than one edge. So that immediately tells you that it's not a simple graph, okay? So if you know that the graph is simple, then you know that the face is surrounded by three or more edges. Okay? That's a big hint. Okay? So we're going to come up with a criteria that could be used to show that certain graphs are not planar, assuming that if it's simple. Okay, so let's say somebody gives you a simple graph. That's easy to tell, right? You just look at every vertex, see if there's more than one connection, then immediately that's a multigraph. But if it's a simple graph, then you know that it's surrounded by 3 or more edges, right? So as you can see over here, this is a simple graph. No two vertices are connected by more than one edge. And every edge that you see has more than 3 edges. Actually, exactly 3 edges, it seems like. So if you look at here, it's 1, 2, 3 edges, right? If you look here, it's again 1 to 3 edges. This one also has 1 edge, 2, 3 edges. And the face that's outside all the graph has 1, 2, 3 edges surrounding the face, okay? Right. It's hard to see how you can say surrounds when it's like inside of this face, but imagine that uh, this is not drawn on a plane, but it's drawn on a very large sphere. Okay, if it's a large sphere, then you can kind of see that this thing extends to the other side and actually connects to one single face. Can you imagine that? Does that make sense? If this is drawn on a balloon, right? Then this other side is really a face that gets connected on the other side, right? And then you can say that the boundary of that face is really 1, 2, 3 edges. Does that make sense? Yeah. So this is an example where actually every face is three edges. Okay. Of course, there are other cases like you can think of planar graph, something like this. And in this example, this face has 1, 2, 3, 4, 5 edges, right? So it's not true that always planar graphs have exactly 3 edges. It could be more, okay? But you have 3 or more edges. Now, let's assume that you count all the edges by going through all the faces and adding up all the boundary edges, okay? If that happens, then the number of edges are counted how many times? So let's see. I don't think I made myself clear there. So let's do this. For this graph, there's F1, F2, F3. There are 3 faces for this graph, right? Okay, so for this F1, I count 1, 2, 3, 4, 5 edges, okay? For this F2, I count 1, 2, 3 edges, so 5 plus 3, okay? And then for F3, I count the one that's bordering this. F3 is outside, right? So the ones that are outside is like 1, 2, 3, 4, 5, 6. 6. Okay, if you add all the edges, then I get 8 plus 6, 14. Okay? How many edges does this graph have actually? Can you count? 1, 2, 3, 4, 5, 6, 7, right? So what's the relation here? If you count all the edges individually that's neighboring a face, surrounding a face, and you add them up, you end up counting edges how many times?
Twice.
Twice, exactly twice, right? So this is really 2 times 7, okay? So here's a nice inequality. So sum of edges of each face is going to be equals to twice of the edges. Okay. Now I know that each face has 3 or more edges neighboring it, right? Edges at the boundary. So if you just wrote down 3 times f instead of counting everything explicitly, would this be bigger than this, equal to this, or less than this? So 3f is bigger than this quantity, less than this quantity, or equal to this quantity? What do you think? For each, so f is the number of faces, right? Just times 3. is this quantity less than this value, equal to this value, or more than this value?
Equal.
No, because some of the faces will have more than 3. Yeah. So what do you get? Sometimes it could be equal, but it could also be. This is what? Is this more or less? You don't get it? Huh?
Less?
It'll be less because, look, this would be like, okay, so over here, if you have 3 faces, okay? What is 3f for this picture?
9.
3 times 3, which is 9, right? What's the actual value of this? We did 5 plus 3 plus 6, right? So this is like 3 plus 3 plus 3 because you're only taking 3. That's the guaranteed minimum, right? So you're just counting the guaranteed minimum, and since the actual numbers are 3 or greater, this value will always be bigger or equal. It could be equal, like this case. In this case, if you count the number of edges, it's exactly the same as 3 times f. I mean, if you double the number of edges, let's do that over here. So here's like 1, 2, 3, 4 faces, right? And each one of these we counted that it has exactly 3 edges, right? So if I count the 3 times 4, that's exactly 12, which is equal to adding up all the 3's 4 times, because every face has exactly 3 edges, right? But now, can you see how many edges there are? How many edges are there? 1, 2, 3, 4, 5, 6. 6 edges, right? That's exactly twice of 12. 6 times 2 is exactly 12, right? Twice of 6 is 8. So in this case, 3f is equals to 2e, but in general what happens is that this 2e is going to be equal or greater. You see that? Okay. So this discussion, this informal discussion, should convince you that if you have a simple graph, it's always the case that 3f is going to be less or equals to 2e. So here's a way to argue. Suppose you're given some graph, and I have no idea if it has a planar embedding or not. So is it possible to redraw this one so that it looks planar? I don't know. But let's say there was, okay? If we succeeded in making it into a planar graph from some given graph, right? Then we know that this will always be true. This will be true because it's planar. And this will also be true because it's simple. So both should be true. Now what you can do is you can take this f, solve this for f. F is 2 minus v plus e, multiply by 3. So that's 6 minus 3v plus 3e. Okay. But we know that 3f is less or equals to what? 2e. So these two together brings you to this inequality. And this inequality can be written again by subtracting 2e both sides, adding the 3v and 6 to the other side. You have this inequality that e is less or equal to 3v minus 6. Now this inequality is a really nice inequality to use because, see, the number of faces is going to be only figured out if you have a planar embedding. Without having a planar embedding just from this graph, there's no way to know what f is, right? But if there is an embedding, then this inequality should be true. And do you see any f here? There's no f. So what that means is that if there's a planar embedding, this better be true. If this is violated, then you know there cannot be any planar embedding. Okay, so here's a nice argument. So theorem: if a simple graph has E greater than 3v minus 6, then it cannot be planar. So let's think about K5. What's K5? You have 5 vertices and you think about all possible connections. So I drew every possible edge between vertices for 5 points. Okay. Now tell me what V is. 5. Tell me what E is.
5.
Well, there's the outside that's 5.
Oh, I would.
10, right? Because there's 1, 2, 3, 4, 5, and then there's the edges that are in here. If you count them, that's extra 5. So E is 10. Now let's see what 3v minus 6 is. This is 3 times 5 minus 6. 3 times 5 is 15. Minus 6, that's 9. Now, is it true that 10 is less or equals to 9? No. Okay. So this inequality is violated, right? Anytime that's violated, or if anytime this happens, then what do we know? K5 cannot be planar. Okay. So that's a very interesting result because before, when I was explaining, oh yeah, K4 is planar, but K5 is not, and I was trying to just argue by like trying out all possible planar embeddings, right? But there was no way to draw it, so we said, oh, it's probably not planar. But here we have a mathematical proof that it cannot be planar. Okay, so it's more convenient this way. However, notice that the graph doesn't say if it obeys this. So this is not to say that if this inequality is obeyed, then it must be planar. So remember that there was this other example where we had the K33. Okay, what is that? You have 3 vertices on this side, 3 vertices on this side, and it's what's known as the complete bipartite graph. Right? Bipartite means you have 2 groups where inside each group there shouldn't be any connections between them. But because this is the most connected simple graph between these 2 groups, it's like this should be connected with all the other members of the other group. This one should be connected with everyone. This should also be connected with everyone. And this one also, we know that it's not planar. You can try so many different ways to make this planar. You see that it can't be done. And for this one, how many vertices are there? 6. How many edges are there? 9, because there's 3 coming from here, 3 coming from here, 3 coming from here, right? So it's 9. Okay, now let's see what 3v minus 6 is. 3v minus 6 is 6 times 3 is 18. 18 minus 6, which is 12. So indeed, 9 is less or equal to 12. Right? This is true. So this inequality is not violated at all. Yet, we know that this is not planar because we tried this so many times, right? Now, interestingly, there's a way to show that this is not planar by using another modification of the Euler characteristics. Okay, so let me try to explain that. So there's a similar inequality. So the inequality that we were using here was, this was the criteria, right? If this is violated, then it's not planar. And this one is not planar, but it still doesn't violate this. So there's a separate one which is applicable for bipartite graphs. Okay, so if a graph, a simple graph is bipartite, then what does that mean? It can't have a triangle. Why is this not a bipartite graph? Do you remember how to tell if a graph is bipartite or not?
Color.
Coloring, right? You color it, see. You look at the coloring. You color this with one color, and then you color this with another color. But then this one has to be a different color for both because it's neighboring. So now you see that the chromatic number of this is at least 3, right? A bipartite graph can always be 2-colored because you can just color one side as red and the other side as blue. And this one, you can see that any adjacent vertices are always different color, right? So we know that if the graph contains a triangle, it can never be bipartite. Okay. So we know that simple graph cannot have a 2-sided one either, right? So this is not allowed, this is not allowed. What does that mean? That means you can at most at least have, you should at least have 4 sides to a face, right? A face, if it's bipartite and you embed it as planar, then it has to have 4 or more edges. Okay. In fact, we know that K23 is planar. So let's think about that one. K23 is, it's like this. And then you can make this planar by like that. Sorry, it's straight. Yeah. So you have 1, 2, 1, 2, 3. So you have a total of 5 vertices. How many faces does this have? It's 1, 2, and then another one, right? And if you look at the number of edges neighboring face 1, it's 1, 2, 3, 4, exactly 4. F2 is 1, 2, 3, 4, exactly 4. F3 has more. 1, 2, 3, 4. Oh, it has 4 as well. 1, 2, 3, 4. Okay. So in this case, every face has exactly 4 edges, right? Yeah. The border of every face is 4 edges. Okay. So that means the inequality that for the simple graph, remember that we had 3f less or equals to 2e, right? Now for the bipartite graph, because this is the least number of edges that a face can have, instead of using 3f, you can use 4f. Okay. And then we can combine this with the Euler characteristics. So first, divide both sides by 2 so that 2f is less or equals to e. Use the Euler characteristic equation v minus e plus f is 2. Bring the solve for f, so f is equal to 2 minus v plus e. Multiply this by 2. 2f is 4 minus 2v plus 2e. And because 2f is less or equals to e, we now have this inequality. And in both cases, the goal is to write an inequality that doesn't have f. Because unless you have an explicit embedding, you don't know what the f is. And by having an inequality, you can use it in the case without having an f, so that you can see if such an embedding is possible or not. Okay. So now if you subtract e and move this 4 and 2v to the other side, you end up with e less or equals to 2v minus 4. And that gives you a nice criteria that if a graph is bipartite and planar, then the following inequality should hold. E less or equals to 2v minus 4. Okay. Now that's actually a stronger statement than the previous one. Okay. See here, 3v minus 6 is probably bigger than 2v minus 4, right? Yeah, that's bigger because v is 3 or more. Okay. So you can say that this is a harder inequality to be satisfied than this one. But that's using bipartite, okay? And now we can use it for this case. So let's see what happens. What is, say v is 6 and e is 9, that's what we had from there. Let's see what we get for 2v minus 4. That's 2 times 6 minus 4, which is 12 minus 4, which is 8. Okay, is it true that 9 is less or equals to 8? No. So this inequality is violated, which means it can't be both bipartite and planar. Because we already know that it's bipartite, K33 is by definition bipartite, that means it can't be planar. Okay, so this shows K33 is not bipartite. Wow, so we have these inequality which successfully distinguished the K5. Okay, successfully show that K5 is not planar and K33 is not planar without having to like draw stuff and say, oh, it's impossible. This is a perfect proof, right? We didn't have to draw things. So now you know for sure that these are not planar. Now, then the natural question you could ask is like, oh, does that mean we can use this for any graph? And the answer is no. And as usual, the Peterson graph is the one that is always elusive. You think something is true, then if you try it on the Peterson graph, it doesn't work. So what's the Peterson graph? So you start with the star-shaped thing, and then you extend the vertices like that, and you draw another pentagon. That's the Peterson graph. Okay, so first of all, you want to see if you can apply this inequality. Can we apply this inequality? And the answer is immediately no, because if you try to do the coloring, see this one required at least 4, I think. Yeah, so you can try, and let's see, if I have, say this is red, and the neighboring edges, these will be blue. Right. And then you could still use red for this guy, but then this one, you can't do either red or blue. So let's say yellow for this one because it's neighboring B and R. And then now over here, because you have yellow, blue, and red, it has to be yet another color that's neither red or blue or yellow, so you need at least another green, and so on. So the chromatic number for this is 4 or more, which means it's not bipartite. Bipartite should have chromatic number 2. Okay. So it's bipartite, which means we can't use that one to prove that this is not planar. Well, let's count how many vertices this has. How many vertices does this have? B is
10.
10, right? You have 5 inside and 5 outside, 10. How about the edges? There's 5 here, there's 5 here, and there's 5 here, so it's total 15, right? Now, because we can't use that one, we have to go with the older version, which holds for any simple graph. Simple graph should satisfy 3b minus 6. And if you plug in 3b, if you calculate 3b minus 6, it's 3 times 10, so 30 minus 6, which is 24. And indeed, 15 is less or equals to 24. So it doesn't violate that inequality, yet this one, we know that it's not planar.
Wait, how come you couldn't use the other one?
Because that one can only be used for bipartite.
Okay.
And we know that if it's bipartite, then the chromatic number should be 2, but we tried to color this and it was at least 4.
Okay.
It's either 4 or 5, yeah. Okay. So now what? So we can't show that this is non-planar just by the inequality. Instead, what you can do is you can show that the subgraph is like a K33. So what you can do is you can delete this edge, and you can delete this edge, and then you can think of these 3 as one side of the bipartite graph, and right, and then these 3 as the other side of the bipartite graph. Let's see if that makes sense. This one goes here. So imagine that oh, maybe it's not this one. Should be this. Okay, good. So think of it like this. If you have ignore these vertices, just ignore that and connect it by a smooth thing. Okay. Ignore this one and connect it by a smooth thing. Now look at what the connection is like. If I say 1, 2, 3, and 1, 2, 3, this one is 1 and 1, so here's like 3, 1, 2, 3, and then the 3 red dots, 1, 2, and 3. Let's look at how 1 is connected. 1 is connected to 1, 1 is connected to 3, and one is connected to 2. Yeah, one is connected to 1, 2, and 3, right? So one is connected to 1, 2, and 3. Okay. Now how about 2? 2 is directly connected to 1, 2 is connected to 2, 2 is connected to 3, right? So 2 is also connected to 1, 2, and 3. Are you following? Yeah. Look at 3. 3 is connected to 1, 2, and then 3. So 3 is connected to 1, 2, and 3. What's that? That is exactly K33, right? Yeah. So if the original Peterson graph can be embedded as a planar graph, then this portion of the graph better be planar as well. Don't you agree? Right? Because this portion is a subgraph of the original one, right? Yeah. The Peterson graph contains this as a subgraph, but this subgraph is like K33, which we know that it's not planar. So that's the proof of showing that Peterson graph is not planar. Peterson graph is not planar because you can find this subgraph, which is isomorphic to K33 if you ignore these vertices, okay? Now, ignoring these vertices means that it's another way to say it is that this K33 is isomorphic to there's a subdivision of this which is isomorphic to this subgraph. That's because of the way we add or subtract vertices. Let's not go too far. I mean, it kind of makes sense, right? Yeah. So that's the proof. That's the harder proof. And this Pearson graph shows you why just having the inequality is not enough for showing such and such is not planar. Okay. So showing planarity is not an easy problem, even with the Krotowski's theorem. Krotowski's theorem, which says if a graph contains K33 or K5 like this, then it's not planar. If it doesn't have any of those, then it is planar. That's Krotowski's theorem, but it's really hard to see a subgraph that looks like K33 or K5. It's not so easy. So even with this Krotowski's theorem at hand, it's not easy to write an algorithm that easily shows you whether a graph is planar or not. So that's why having inequalities like this one for general simple graph and this one for bipartite graph is useful, right? But those things have the limitations. So in the examples of Pearson graph, you actually have to work quite hard to find something that shows it's non-planar.